Let me ask you a question. Why don't you fall right through the floor? No, I'm serious. Atoms are almost entirely empty space, so what's actually stopping your hand from just passing straight through your desk?
Well, the answer comes from one of the sharpest, most critical, and frankly, one of the most intimidating minds in the entire history of physics.
So let's dive into the story of Wolfgang Pauli, a true architect of our quantum reality, and the very person who figured all this out.
You see, Pauli wasn't just smart. The guy was a prodigy who pretty quickly earned the nickname the conscience of physics. And his story, well, it starts incredibly early.
How early, you ask? Get this. At just 21 years old, he was asked to write a little encyclopedia article on relativity. What he turned in was a 200-page masterpiece, so profound that it left Albert Einstein himself absolutely stunned. Yeah, that pretty much set the tone for his whole career.
But his most legendary contribution came when he tackled a massive crisis in the world of physics. He came up with the rule that, and I'm not exaggerating, literally shapes reality itself. It's called the exclusion principle.
Okay, so by 1925, physics had totally hit a wall. Scientists couldn't figure out how electrons arrange themselves. I mean, why didn't they all just collapse into the nucleus of the atom? And the periodic table, why did it have that very specific repeating structure? Nobody had a clue. And Pauli's solution? It was breathtakingly simple. Just think of an electron's quantum numbers as its unique address in the universe. Its energy level, its orbital shape, stuff like that. Pauli basically said that in any single atom, no two electrons can ever share the exact same address. It's like a cosmic game of musical chairs, where every single electron has to have its own unique seat. Period.
Now, this one simple rule has absolutely staggering consequences. It's what forces electrons into higher and higher energy shells, which in turn dictates the entire structure of the periodic table, and with that, all of chemistry as we know it. It's what gives matter its structure, its stability. It's the literal reason your hand doesn't pass through your desk. And get this, on a cosmic scale, this exact same principle is what prevents massive stars from collapsing under their own immense gravity.
You don't have to take my word for how important this is. The great physicist Richard Feynman summed it up perfectly. He said, if all of physics were lost and only one statement could be preserved, the Pauli exclusion principle would be the one worth saving. Now that is a serious endorsement. But here's the thing. Pauli was no one-hit wonder, not even close. He went on to solve even deeper puzzles, including a bizarre property called spin and a mysterious ghost particle he was genuinely worried would never be found. So, when physicists first suggested that electrons have an intrinsic spin, it's not a literal spin, but more like a built-in magnetic compass needle, Pauli was, true to form, pretty skeptical. But once he was convinced, he did what he did best. He built the hardcore mathematics for it. His spin matrices became an absolute cornerstone of quantum mechanics, giving a perfect description of this fundamental property. The next huge headache was something called beta decay. It's when a nucleus spits out an electron. Now, the law of conservation of energy said that electrons should pop out with a very specific, predictable amount of energy. But when they ran the experiments, they saw a total mess, a continuous, sloppy range of energies. It looked like energy was just vanishing into thin air. And that breaks one of the most sacred rules of physics. To solve this, Pauli came up with what he himself called a desperate remedy. He was so uneasy about it that he wrote in a letter, "I have done a terrible thing. I have proposed a particle that cannot be detected." He basically imagined that some tiny, neutral ghost particle was secretly flying off and carrying away that missing energy. And that ghost particle? Well, that was the neutrino. It took decades, but it was finally detected, proving Pauli's wild intuition was spot on. Today, the neutrino is a fundamental piece of the standard model of particle physics. His terrible thing turned out to be another revolutionary insight. But Pauli's legacy isn't just about his world-changing discoveries. It's also about his relentless, ferocious demand for intellectual honesty, the very thing that earned him the title the conscience of physics. He was famously critical of any sloppy or unclear thinking. His most legendary put-down, which he saved for ideas he thought were completely baseless, was this: "That is not right. It is not even wrong." What he meant was the idea was so incoherent, so untestable, that it wasn't even worthy of being called wrong. It was a brutal but incredibly effective form of quality control for science.
And when you step back and look, his impact is truly everywhere. The exact same principle that explains chemical bonds inside a molecule also explains why neutron stars don't collapse. His ghost particle became a foundation of our entire standard model, and the rules he laid out for how electrons behave are the basis for every semiconductor chip inside all our modern electronics.
I mean, just look at this timeline. It's wild. In 21, he basically schools Einstein on his own theory. Just 4 years later, he figures out the rule that governs all of matter. By 1930, he's straight up inventing new particles. So yeah, it's really no surprise that in 1945, the Nobel Prize in Physics was his. This wasn't just a career, it was a lifetime of one foundational insight after another.
In the end, Wolfgang Pauli's work is invisible architecture holding up our entire modern world. From the smartphone that's probably in your pocket to the distant stars in the night sky, his principles are quietly at work holding reality together. And that really leaves us with one final thought. What's more essential to making real progress? The revolutionary idea itself, or the kind of relentless, uncompromising intellectual integrity that Pauli represented? The kind of integrity you actually need to discover that idea in the first place.